Hello friends, welcome to YouTube channel Electronics. In this video, we will learn enhancement type MOSFET. In earlier video, we have discussed BJT. We have also discussed JFET, junction field effect transistor, and MOSFET, metal oxide semiconductor field effect transistor, also called IGFET, insulated gate field effect transistor, their types and depletion mode type MOSFET in detail. So in this video, we will focus on enhancement type MOSFET. MOSFETs have three terminals named as gate, drain and source. In a depletion mode MOSFET, there was a default N-channel between source and drain terminals, so it is normally on. Hence, even at 0 gate voltage, there would be a current flow between source and drain terminals. While in enhancement type MOSFET, there is no default channel is present between source and drain terminals. Hence, it is normally in off condition at 0 gate voltage. Let's discuss the construction of a N-channel enhancement type MOSFET. Just take a block of lightly doped P-type semiconductor. This block will be a base for MOSFET. We also call it as substrate. The entire MOSFET will be fabricated on this substrate. Next, two heavily doped N-type semiconductors are diffused on this substrate. Source and drain terminals are brought out through metallic contacts from these two N regions. Now the entire surface of the substrate is coated with an insulating layer of silicon dioxide. On this layer of silicon dioxide, a thin metallic plate is placed and a gate terminal is brought out from this metallic plate. If we observe over here, the gate terminal is insulated from substrate and there is no default N-channel present between drain and source. A P-channel enhancement type MOSFET is similar in construction, except it uses a lightly doped N-channel substrate and two heavily doped P regions are diffused on it. Source and drain terminals are directly connected from them. Here also, gate terminal is insulated by silicon dioxide, unlike source and drain contact, and there is no default P-channel present between source and drain. This is the constructional feature of a P-channel enhancement MOSFET. In some MOSFETs, the substrate terminal is also available externally. If we observe over here, there are two diodes formed in this MOSFET. One is between source and substrate and the other is between substrate and drain. If we see the electronic symbols of the enhancement type MOSFET, they replicate the actual construction. It shows all the terminals. Here, this dashed line at drain, source and substrate terminals indicates the channel. Basically, the dotted lines indicates the absence of the continuous channel. Further, there is a space between gate terminal and the channel. This indicates the gate terminal is isolated from the channel. In some MOSFETs, substrate terminal is also available. So, in that case, MOSFETs are represented by these symbols. Now, if you observe the N-channel and P-channel MOSFETs, then the only difference is that the direction of this arrow. If it is going inwards, then it indicates N-channel MOSFET. If it is going outwards, then it indicates P-channel MOSFETs. Basically, the arrow position indicates the direction of current flow. In most of the MOSFETs, substrate terminal is internally connected to the source terminal. So the source and substrate terminals are always at same potential. Then we can say that only one diode junction is formed in the MOSFET. In that case, these symbols are used. Here we can see that substrate terminal is not shown. It is shorted to the source terminal. Now let's see the operational features of enhancement type MOSFET. Here the majority charge carriers in these source and drain regions are free electrons. If we apply a DC voltage VDS between source and drain terminals like here, positive to the drain and negative to the source terminal, as there is no conducting channel between source and drain, hence there will be no current will flow from source to drain. Moreover, the PN junction between substrate and drain will be reverse biased because of the applied positive voltage at N-type drain and applied negative voltage at P-type substrate. Hence, as we increase the voltage VDS, the depletion region between the drain and substrate will get increases due to reverse bias action of drain and substrate PN junction. Here we haven't applied any voltage at the gate terminal, or we can say that the gate voltage is 0, or we can assume that the gate and source terminals are connected together. So the voltage between gate and source VGS is equal to 0. So we can say that at 0 gate voltage, or when VGS equals to 0 volts, due to absence of conducting channel between source and drain, there will not be any current flow through this enhancement type MOSFET. This is called the cutoff region of MOSFET. Now to flow current between source and drain, we have to create a channel between them. To create a channel, let's apply a small positive voltage of VGS at gate terminal. This substrate is a P-type semiconductor. Hence, holes are majority charge carriers, but there exists some free electrons as minority charge carriers. Because of the insulated SiO2 layer between gate and substrate, the positive voltage at gate terminal cannot flow to substrate. So, positive charge will develop at gate terminal. If we observe over here, this portion of the gate and substrate behaves like a capacitor because there is a dielectric material between conductor and semiconductor. So the positive charge at gate terminal will attract the electrons in the substrate towards it, and at the same time it repels the holes away from it. In short, what happened here is that negative charge developed in this part of the substrate. This will form a channel of negative charge carriers even inside P-type substrate. So the inversion layer of free electrons formed between source and drain, and it connects source and drain with each other internally so that the electrons can move from source to drain. Hence, it will constitute current flow through this channel. So the value of the gate to source voltage VGS at which this inversion layer is getting created is known as the threshold voltage. And whenever VGS is less than this threshold voltage, there will not be any flow of current through the enhancement MOSFET. Remember, here we are thinking about movement of electrons, but the conventional current or holes flows in opposite direction. So here the conventional current flows from drain to source terminal. Let's say the conventional current that is flowing into the drain terminal is called ID, and the conventional current that is flowing out from the source terminal is called IS, and we can say that this ID and IS are equal. The thickness of this inversion layer can be controlled by changing this gate voltage. As we increase the voltage VGS, or whenever VGS is greater than VT, then more positive voltage will develop at the gate terminal. It will ultimately increase the width of the inversion layer in the substrate. Now, if we increase this drain to source voltage VDS, then more number of free electrons can easily move from source to drain because of the increased channel width of the inversion layer, and in this way current flow increases in the MOSFET. If we represent the current ID versus VDS in a graph, ID in x-axis and VDS in y-axis, initially it will looks like a straight line because as we are increasing the source to drain voltage VDS, the drain current ID will also increases linearly. Now the MOSFET is in ohmic region or linear region because it follows Ohm's law. That is, as the voltage increases, the current increases linearly. But along with this channel, there will be a depletion layer around this channel because if you observe, there are two PN junctions in this MOSFET. But here source and substrate terminals are internally connected. So only one PN junction is formed in this MOSFET, that is between drain and substrate. Now if you observe the potentials at this drain and substrate PN junction, drain or N channel is connected to positive terminal and substrate or P-channel is connected to negative terminal of this voltage VDS. Hence this drain and substrate PN junction is reverse biased. Because of this, the depletion region appears across the junction. But as we increase this voltage VDS, due to the positive voltage at the drain terminal, this PN junction will get more reverse bias. So the depletion region between the drain and substrate will increases. Also the width of the channel has been reduced towards the drain side. Now due to this narrow gap of the inversion channel, there is a restriction of flow of charge carriers through it. Hence the current flow will reduce. This reduced current flow can be seen in this graph. Here the slope of the line changes and it becomes more and more horizontal. As we keep on increasing this voltage VDS, a point will be reached where the channel is completely pinched off. This is called the pinch off effect. But in real cases, the channel is not completely pinched off due to the large flow of electrons. Hence, instead of stoppage in current, there is a constant current will flows through the channel. This current is known as saturated current and the voltage at which occurs is known as saturation voltage. Now, if you further increase the voltage VDS, the reverse bias will increase and the channel width will further reduces, but the current flow will not changes because it's saturated. So here in this output characteristic curve, the slope of the line changes and it becomes horizontal. This saturation current value can be represented as IDSS. But if you want to increase the current flow in the MOSFET after the pinch off condition or saturation current, we must increase the voltage between gate to source, that is VGS. As we know that the thickness of this inversion channel between source and drain can be controlled by changing gate voltage. Here, because of increased positive charge at gate terminal, there will be increased in the width of the inversion channel in the substrate. So in this way, we can increase the current flow in the enhancement MOSFET. We can draw this in output characteristic graph. For the increased positive value of voltage VGS, the drain current ID will be even more than this saturation current. If we draw the drain curves for the different values of VGS, then it will looks like this. So as you can see here that as the value of gate voltage VGS is increasing, the drain current ID will also increasing. Now let's see the relationship between different values so that we will get clear understanding of this concept. As we know, whenever VGS is greater than threshold voltage VT, we will get pinch off condition. If you observe over here, both gate and drain terminals are at positive potential, so there will be less voltage difference between them. This can be expressed as VGS minus VDS. In this equation, source is common for both VGS and VDS, so it can be omitted. So we can write expression as VG minus VD. Suppose if we increase this voltage VDS, then the drain terminal becomes more positive. So the potential difference of VG minus VD will decrease. Now drain is at more positive potential and source is at negative potential. So due to this part of the gate region which is towards the drain side will be at less positive potential with respect to drain. On the other hand, this part of the gate region which is towards the source side will be more positive with respect to source. Hence this part of the gate region have less capacitive action. Hence fewer electrons will be attracted towards the gate terminal. Because of this, channel width gets narrower as compared to source region. And as we keep on increasing this voltage VDS, then at one particular voltage the pinch off condition will occur. This particular voltage VDS is known as saturation voltage, and this saturation voltage can be expressed as VGS minus VT, where VT is the threshold voltage. That means pinch off condition will occur whenever the difference between voltages at gate and drain are just equal to the threshold voltage. At the threshold voltage, or whenever VGS equals to threshold voltage VT, the channel is just being created between the drain and and source terminal. So for the fixed value of VGS, if you further increase the value of VDS, the voltage difference between the gate and drain terminal will be even lesser than the threshold voltage, and due to this the channel will not get formed towards the drain terminal. So the current through the channel should be 0. But actually we know that after the pinch off condition there will be a constant saturation current will flows through the MOSFET. Any further increase in drain to source voltage VDS makes no sense. This is because the electrons passing through this channel can still be able to create a narrow gap due to their electric force. So after the saturation voltage VDS, the drain current through the MOSFET remains constant. So if you draw the drain curves or ID versus VDS curves for the different values of VGS, they will appear like this. So here we can observe that as the gate voltage VGS is increasing, the drain current ID will also increasing, and we can draw a parabolic curve to show the locus of voltage VDS where the drain current ID will get saturated for different values of VGS. So in this graph, this region is known as the linear or ohmic region. So in this region, the MOSFET operates as a voltage controlled resistor. This is because for a fixed value of VDS, as we change the voltage of VGS or VGS is greater than VT, then the width of the channel will change, or we can say that the channel resistance will change. So whenever VGS is greater than VT and the VDS is lesser than VGS minus VT, in that case the MOSFET operates in ohmic region. So it can be operated as a voltage controlled resistor. Next region of operation is the cutoff region. Whenever this gate voltage VGS is less than threshold voltage VT, then there will not be any conducting channel formed between source and drain regions. So due to absence of channel, the MOSFET remains in the off condition. So the cutoff region shown in this graph as 0 drain current ID. It happens whenever VGS is less than VT. Next region of operation is the saturation region. In this region, the drain current ID is constant. Whenever this drain to source voltage VDS is greater than or equal to VGS minus VT, at that time MOSFET remains in pinch off condition and the drain current becomes constant. This constant drain current is denoted in the graph. This region is known as saturation region. This is all about the different regions of operations of MOSFET. Now let's see the transfer characteristics of enhancement type MOSFET. The transfer characteristics defines the relationship between input and output quantity. Here it defines relationship between output the drain current ID and the input the gate voltage VGS. Basically it shows how the drain current ID changes as we change the gate voltage VGS. Here the drain voltage VDS is kept constant, and we can observe that up to the VGS reaches to the threshold voltage, the drain current ID is 0. As we are increasing the gate voltage VGS, then the drain current ID will also increasing. The relationship between ID and VGS can be given by the expression ID equals to K times VGS minus VT whole square. Here K is device constant. It depends on the physical parameters of the device. So by using this expression, we can find the value of drain current for the different values of VGS. This is all about N-channel enhancement type MOSFET. Now let's briefly discuss about P-channel enhancement type MOSFET. In P-channel MOSFET, free electrons are the majority charge carriers in the substrate and holes are majority charge carriers in drain and source regions. So the polarity of the applied voltages will also gets reversed. That means this voltage VGS is negative. So the negative charge develops across the gate terminal. This will attract the holes in the substrate towards it. In short, positive charge developed in this part of the substrate. The value of the VGS at which this inversion layer is created is known as the threshold voltage. So VGS must be greater than threshold voltage VT to create inversion layer barrier between source and drain. The current starts flowing through the MOSFET whenever we apply the negative voltage VDS between the drain and the source terminals. But here the movement of charge carriers are holes, so the conventional current also moves in the same direction. Let's say the conventional current flows into the source terminal is IS and the conventional current flowing out from the drain terminal is ID. Here we know that ID equals to IS. Here also, as we increase this voltage VDS, the pinch-off condition will occur in the MOSFET and the current flow gets saturated. This pinch-off condition occurs whenever minus VDS equals to minus VGS minus of minus VT. Here all the voltages will be negative. Now for the P-channel enhancement MOSFET, if you see the drain or the output characteristic curve, then it will look like this. But here this voltage VDS and the gate voltage VGS will be negative. As we can see from the graph, as the gate voltage VGS becomes more and more negative, then the drain current ID will increases. And whenever the gate voltage VGS is greater than the threshold voltage VT, then the MOSFET will operate in the cutoff region. Let's see the transfer characteristics of P-channel enhancement MOSFET. It looks just opposite to the N-channel MOSFET. It shows how the drain current ID changes as we are changing the negative gate voltage VGS. That's all about enhancement mode MOSFET. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.